Welcome to part 2 of the Edexcel IAS Chemistry Unit 2 Specification Revision. It's been a while since the last video, very many months actually. But yeah, from today, there's going to be daily videos on chemistry and other subjects as well, in order to complete this whole revision, okay? So let's begin from 6.8. We are not starting with 6.7 because that is Unit 3. So in our Unit 3, we'll cover the core practicals and the further suggested practicals, okay? So let's start with 6.8. Be able to evaluate the results obtained from experiments and comment on sources of error and uncertainty and any assumptions made in the experiment. Okay, so what this basically means is when we have a calorimeter, let's look at it like this. This is the lid. There is a thermometer inside. There's a stirrer and there's heat, okay? Let's add insulation on the side as well. This is like a basic calorimeter, okay? What we will see is, let's say we're using this to find the enthalpy change in a specific reaction, okay? And we get an enthalpy change that is far greater or slightly greater than the textbook value, okay? A question in Unit 2, so in Unit 2 or in Unit 3, can be, why does this occur? Why is this the case? Well, this is due to experimental error. So more heat is required because more heat is lost, okay? There is heat loss. One way can be through the lid. So let's say the lid is not present. So, due to evaporation, heat loss will be there. Or let's say there is no insulation at the side. So we can say heat loss is there due to conduction. Let's say this, the side is touching the floor, okay, or the heater, so there can be heat loss through there. Let's say it's a perfect system, okay, there's everything. Even then, there will be some level of heat loss, with the container, with the thermometer, there will always be a certain, it's never 100% accurate, okay, so there will always be heat loss. So that's the sources of error part, okay. We have drawn graphs on cooling curves in the previous example. I think, let me just draw it really quickly. It looks something like this, and then like this. So it looks like that, and then you have to extrapolate the graph and everything. We've explained that in the previous video. But yeah, moving on really quickly. 6.9 now. Understand the term bond enthalpy and mean bond enthalpy. So bond enthalpy is probably one of the most important things not one of the most important things you need to do, but you will occasionally see 5-6 mark questions on this. So what is bond enthalpy? Bond enthalpy is the averaged, it's important to say averaged, that is not how you spell average, sorry. Averaged energy required to break 1 mole of a stated bond in gaseous state under standard conditions. Now, if you've noticed the theme, there is always going to be standard conditions. Whether you're doing enthalpy of formation, standard enthalpy of fusion, there's always going to be standard conditions of 298 Kelvin. This is the temperature and pressure of 1 atmosphere, okay? So it's important to always know this. Again, whenever we're doing something averaged, we are most likely taking the gaseous value, okay? The gaseous state of it, okay? So yeah, that is basically what bond enthalpy means. Mean bond enthalpy values will tell you how much energy is required to break a particular bond averaged across a range of compounds containing that bond. What do you mean by this? If we have 4 CH bonds, this is methane, okay? Methane is CH4, which looks like this. This is not how it's actually a tetrahedral, but like I've drawn it in a 2-dimensional plane, which is not how it's supposed to look like. Anyways, yeah, so continuing. When we have 4 of these, the mean bond enthalpy, so mean bond enthalpy will be the average value for the CH bond. So your mean bond enthalpy will only give you one value of this, but it's averaged amongst all these, okay? Let's say the first CH bond takes you know, X, uh, X joules, okay? The second CH bond takes X plus 1 joules. The third one gives X plus 2 joules, okay? The average amongst all this will just be X plus 1. Yeah, so that's basically the concept behind it. But yeah, we can just take that. It has restarted, okay? So we can just go back to it really quickly. Okay, that is not the correct one. It is this, okay. Yeah, so let me just open the other one as well. Sorry for this, by the way. Yes, so continuing now from where we left off. That is mean bond enthalpy done. So 6.10, be able to calculate mean bond enthalpy from enthalpy changes of reactions. Okay, so enthalpy change of reaction, let's just give it E reaction, will be equal to, so this is delta H of the reaction, delta H reaction will be equal to the summation of the enthalpy of the bonds broken, so the energy of the bonds broken, minus the summation of the enthalpy of the bonds formed, okay? Now it's important to know that when you are breaking a bond, let's look at it like this, and when you're forming two bonds. So the way I look at this is, let's start with bonds formed. When you are combining these two together, the gap between them is removed, okay? So this is how I remember it, by the way. The gap between that two is removed. So let's, look at that gap as energy. So let's say energy is removed. Obviously, this is not what actually happens, but this is just the way that I remember it, okay? So yeah, so bonds formed will be energy released, okay? So that has a negative value, which is, it's exothermic, right? Energy released is exothermic, which is negative enthalpy change. So that's why we have the negative value here. And then bonds formed, bonds breaking, you obviously can't break something on its own. You need to give it a certain energy and then it'll break. That's why it's a positive value, okay, of bonds broken. Let's look at an example. This example is from the Physics and Maths Tutor website. So CH4 plus 2O2 to give us CO2 plus 2H2O. When you're given this now, this is going to be a 3-mark question, okay, at the most. But they can give you a 5-mark, 6-mark question on this. So it's very easy to lose a lot of marks here. So let's go step by step. Yes, this is going to be time consuming, but it is the best case that you can do to ensure that you get as many marks here, okay? First thing we do is look at the table given, okay? There's going to be a table given of the bond and the bond enthalpy. Enthalpy in kilojoules per mole, okay? There's going to be the CH bond, the O double bond O, O single bond H, and the C double bond O. This is 413, this is 498, this is 464, and this is 799, okay? What we do is first we write this in the drawn form, okay? So it's going to look like this. This is CH plus 2O2, okay? You get carbon double bond, so you get carbon plus 2OH, okay? Now we can look at this in a better way. Here we can see that there are 4 CH bonds, plus here we can see there are 2 O double bonds. Here we can see there are 2 carbon double bond O bonds. And here we can see there's 2, but there's also 2 here. That's what I'm saying. It's very easy to lose marks here because people sometimes just think there's 2 here and, oh, let's write 2 OH bonds. But as we can see, there's 2 here, and there's also 1, 2, okay? So there's going to be a total of, 2 times 2. So there's going to be a total of 4 OH bonds there, okay? We can use this and the equation that we got up here, this equation, to find our answer. So the summation of the bonds broken is on the left side, which is this. This is broken to form these, right? So let's look at this side. I've drawn too many circles, but I need to erase that. Okay, so 4 carbon single bonds is going to be 4 times 413 plus 2 times 498, sorry. This is the enthalpy of the bonds broken. The enthalpy, the summation of the enthalpy of the bonds formed is going to be 2 times the carbon single bond, carbon double bond O, 799, plus 4 O single bond H, which is 464. When you put this in the calculator, you're going to get 2648 here minus 3454 here to give you a enthalpy change of reaction of negative 806 kilojoules per mole. Okay, this tells us that the reaction is exothermic, hence, yeah, so that is how we calculate it. That's a simple calculation, but with practice you will get a better understanding of it. Okay, yeah, so the last part for this video, understand that bond enthalpy data gives some indication about which bond would break first in a reaction, how easy or difficult it is, and therefore how rapidly a reaction will take place at room temperature. Let's say we're given reaction 1 R1 and R2. Reaction 1 has an enthalpy of reaction of, let's say, plus 9,000 kilojoules per mole. Okay, that's very high, by the way. And let's say reaction 2 will have a enthalpy of reaction of negative 9,000 kilojoules per mole. Okay, this reaction and this reaction, let's see what it means. The positive 9,000 will tell us that this reaction is endothermic. 9,000 kilojoules will be required for every 1 mole, okay, of the reaction, reactants for the reaction to take place. Here, 9,000 kilojoules is released every time 1 mole of the reactant reacts, to form 1 mole of the product, right? So based on that, we can tell that this reaction is much more likely to occur than this reaction, because this reaction you need to feed energy for that value to be reached, then only the reaction will take place. Here, this is the energy released. So that is not, the exothermic reactions are always more likely to occur, and the higher, by that I mean the lower negative. So, the higher exothermic, by this I mean that it is more negative. So more negative the enthalpy H is, the easier it is for the reaction to occur. Okay, so yeah, that is that. In our next video, we're going to look at intermolecular forces as one video, and then redox chemistry in group 1, 2, 2, and 7 as the next video after that. But yeah, chemistry unit 2 is a lot, as we can see here, but we will cover all of this and finish chemistry unit 2, which ends around here, I think. Yeah, it ends here, and then we'll begin unit 3 chemistry. But yeah, from now on there'll be a new video every day. This is it for this video.